Okay, let's go ahead and start the class. Last week we were talking about conservation of mass and momentum equation, and we are going to continue that discussion. But before talking about the conservation of mass, let's talk about the class time. Jude right here reached out to me about the class time and wanted to see if we can actually change the class time to an earlier time on the same day. You should have received an email from him earlier.
Are you guys interested in changing the time?
Yes. And this must be a unanimous agreement. So everyone has to be on board with this. I mean, we don't really want to have a vote because we don't want to intimidate people who don't want to change the class. So let's do this. If you have any reservations about changing the class time, just send me an email. I'll make sure that you remain anonymous. And even if I receive one email, we're going to keep the class time as is. But if not, then we're going to see if we can find a suitable class time to replace the time we have. Yes.
If there were to be like an alternative time to be given, like what would that time be?
That is the second next step. The first step is to make sure that everyone is on board with this.
I would have to know.
I have to know if everyone is on board, then we are going to move on to finding a suitable time. If we can find a suitable time, we're going to keep the class time. Okay? So if I don't receive an email from you, it means that you are open, but that depends on the time. Okay? Does this make sense to everyone? Okay, so again, if you don't want to change the class time, just come to my office, talk to me, and or send me an email. Your classmates will not know that you didn't want to change the class time, and if I don't hear from anyone, I will wait until Wednesday, I guess. If I don't hear from anyone, then I will propose a couple of time slots, and then we can vote on the time slots, right? That will work, okay?
So if we cannot fit the time slot, the class is going to be the same, right?
Classroom?
No, like I can change to another time slot, but maybe not to all the time slot.
Yeah, no, the time slot has to work for you.
Okay.
That's all right. I mean, and it has to work for everyone, not just you, right?
Yeah, sure. But do you mean what? Do you know?
But if the time slot, I don't know yet. I'm just waiting for everyone to see. There might be some people who don't want to change the class time at all, right? Okay. Okay. So let's move on. Conservation of mass. We started talking about the conservation of mass. We talked about the Reynolds transfer theorem. And we are going to start from the beginning. And I guess go from there. So conservation of mass. The idea is Whatever mass comes in has to go out. Mass is neither created nor destroyed. That's the idea of conservation of mass. Just to recap everything, we talked about this control volume, right? Let's say there is mass coming in from this side and from the top, and there is mass going out from here. Let's have numbered boundaries. So, what is the conservation of mass for this control volume? M dot 1 plus M dot 2 is equals to M dot 3 plus M dot 4, right? We can move everything to one side and get M dot 3 plus M dot 4 minus M dot 1 minus M dot 2 equals to 0. Conservation of mass, right? Plain and simple. There are a couple of assumptions hidden in this formulation, but we don't even need to discuss the assumptions of this one. Okay. So how do we calculate these mass flow rates though? Density times area times velocity, right? The formula for mass flow rate is density times area times velocity. Well, what does this formula assume? It assumes that you have uniform velocity at each boundary and uniform density, which essentially means that you have velocity distribution, the same velocity at any location, and the same density at any location. This is the assumption you're making. Or you're using average values, average of density and average of velocity. What if we can't make this assumption? What will happen then? Which essentially means that it is the same control volume. Let's say the velocity distribution is like this. We won't be able to calculate the mass flow rate by using the local velocity, by using rho AV. So what should we do then? We have to use the integral or differential perspectives. Essentially, we have to choose a small element in our boundaries and go from there. Choose a small element. Choose this. Let's take a look at this sliver of flow here. The idea here is that the velocity here is rho. That velocity is v, density is rho, and the area is the dA, the derivative of area. A small area analysis. Okay? This is the mass flow rate through a very small element of this inlet. How can I find the mass flow rate throughout the inlet? Using this information, rho v dA. Integrate along over the area, right? It can be a duct, it can be a circular thing. Integrate over the area. So, since we are integrating over the area, it's an area or double integral, right? Mass flow rate over the whole surface here is going to be equal to double integral of rho v dA. Okay? And the same is true for all of the other boundaries. So over the boundary 1, boundary 2, boundary 3, boundary 4, minus boundary 1. Doesn't really matter. Just want to remain consistent with the previous cases. This has to be equal to 0. Okay? So this is going to be the general form of conservation of mass for a steady state case. Okay? But is there any way for us to combine all of these integrals into just one integral? Essentially just have one equation that is not dependent on the number of boundaries, number of inlets and outlets. So if you want to use this formulation, if you have 3 inlets and outlets, you're going to have just 3 terms here. If you have 5, you have to have 5, right? But we want to come up with a formula that is general enough, or very general as possible. How can we make this even more general? We have already made one assumption that this is uniform velocity, uniform density. We didn't make this assumption when finding these formula, and we want to make the conservation of mass equation even more general. Let's take a look at this control volume again. We have the direction of the flow, inlets, and 2 outlets. To find a more general formulation of conservation of mass, you have to look at the differences between these formulas. So these are, for the inlets, we have negatives, and for the outlets, we have positive. Other than this sign, everything else is exactly the same for this formula. Right? It's the exactly same formula. The only difference is the sign. So if we have a way, if we can find a way that our formulation can determine the sign automatically based on the fact, based on whether it's inlet or outlet, we have found our general formulation. So do we understand where we are going with this? So we want to find a way to determine the sign of these integrals automatically. And to do so, let's talk about the surface normals. Do we know what a surface normal is?
Pressure acting normal to the surface.
I mean, it's not a pressure. It's the characteristics of the surface. Surface normal, right? What is it? It's essentially just a normal, it's the unit vector that is normal to your surface, right? And that is a characteristics of the direction of your surface. The surface normal is always normal to the surface and is always pointing outward in a control volume. So surface normal for these is going to look like this. Again, surface normal n hat, it is a unit vector, meaning that the magnitude of it is 1 and is always normal to the surface and always points outward on these surfaces, right? These are the surface normals. Okay, so we have the velocity direction, velocity vector. We have the surface normal. Let's take the dot product of between these 2 vectors. Dot product of the 2 vectors. For this, dot product of v and hat. Oh, you don't see what's going on? What happened? Dot product of v and hat. How do we find the dot product of 2 vectors? Their magnitude multiplied by each other multiplied by the cosine of the angle between the 2, right? Magnitude of velocity, magnitude of the n hat vector, and multiplied by the cosine of theta between the 2. Magnitude of velocity is just velocity. What is the magnitude of the surface normal? It's a unit vector. So what is it? 1, exactly. And what is the angle between these 2? 180 degrees, exactly. What's the cosine of 180 degrees? -1. So this dot product is going to be negative v, right? See? Surface 1 has a negative sign. So if we replace our velocity with this, the dot product of velocity and surface normal, what you're going to end up with, depending on the surface, is going to be your velocity and its respective sign. Does it make sense? There's nothing special to it. We just do this because we want to find two things. First of all, the inlets and outlets. We care about the movement normal to the surface, right? And also the sign. So we can rewrite this whole equation as the double integral of density, the dot product of velocity, and multiplied dot product by n hat, the surface normal, derivative of area, has to be equal to 0. And then you should apply this. You have to apply this to all of the inlets and the outlets. If you apply it to this number 1, it's going to give you negative double integral of rho v dA, right? If you apply it to number 4, it's going to give you positive double integral of rho v dA, right? Conservation of mass. Okay. Any questions? Okay. This is one way of looking at things. But during the last lecture, we started using the Reynolds transport theorem, right? Which is going to end up giving us the same equation for the conservation of mass, but from a different perspective. Let's use that perspective again. Reynolds transport theorem. This was the general formula for Reynolds transport theorem. The rate of change of a variable of a system is equals to the rate of change of that variable over a control volume plus the fluxes out of the control volume or into the control volume. See, this looks very similar to what we have here. The only addition here is B. Yeah. So this B can be any parameter. It can be temperature, can be momentum, can be mass, whatever, right? And B, capital B, divided by mass of the system is going to give you a small b. This is just the theory. We did talk about this theory a little bit. At the end of the day, you don't really need to understand where it comes from, or you don't really need to prove it. You just have to know that it exists. And it is the Reynolds transport theory. Okay. So the idea is using this theory, we can find the conservation of mass, the momentum equation, and the energy equation. Let's use this to find the conservation of mass. So what is our parameter here? The parameter B, capital letter B, is going to be mass of the system, which will make the small letter b just 1, based on the definition. Right? Okay? So let's just substitute b for m and 1. The rate of change of mass of the system is equal to the rate of change of mass of the control volume plus the fluxes out or into the surfaces, or control surfaces, inlet and outlet. So for control surface, the double integral, we use CS, control surface, not control system, control surface, control volume, and system. This is a general form of conservation of mass from the Reynolds transport theory perspective. So what did we say about a system? Well, how did we define a system?
Constant mass.
constant mass. It's a selection space which mass doesn't change, right? Okay, so based on this definition, what is the rate of change of mass in a system? Zero, right? So 0 is going to be equal to the rate of change of our mass over the control volume. And whenever you mention this is a control volume integral, you don't need to use the 3 integrals. You can just say integral over a control volume. That is essentially, that means a triple integral. The same is true for a double integral. Okay. General form of conservation of mass. Let's take it a little further. Let's talk about an incompressible flow field. What does an incompressible flow field mean? Yes. Density does not change. So, what can you say about this first term on the right hand side of the equation? We're talking about rate of change of density over the whole volume. Incompressible flow field, this has to be 0, right? I mean, it's constant, its rate of change is 0, right? So, for an incompressible flow field, conservation of mass becomes double integral or integral over the control surfaces of rho v and dA equals to 0. Exactly the same equation as we had here. These double integrals are also called fluxes. So in terms of a mass conservation problem, it's a mass flux. Momentum conservation problem, it's a momentum flux. The double integral over a surface is always going to give you the flux of something. It can be flux of temperature or anything. Any questions? Okay, so this is the integral form, these two. This is the general, I guess, for any flow field, compressible or incompressible. And this is the flow conservation of mass for the incompressible flow field. And this is the integral form of conservation of mass. Okay. The next step for us is to take this integral form and find the differential form of conservation of mass in a fluid flow problem. Okay? How should we do that? The first thing you want to do, and we're going to use this formula. We're going to use the more general formula. Let me rewrite it here. The first thing you want to do in finding the differential form of these equations is to combine the two integrals. How can we combine these two integrals? What comes to your mind? One is an integral over the area, the other one is an integral over volume. So one is a triple integral, one is a double integral. What do you guys think? 2 bonus points for a correct answer. Can I ask the question again? You get negative 2 bonus points. We want to find the differential form of this conservation of mass equation. They said the first step is to combine these integrals, essentially to have just one integral. We have 2 integrals. Now, the question is, how can we combine the 2 integrals? You can look up the lecture notes. The answer is in the lecture notes, in the mathematics review. Yes?
You take the derivative of the control volume with respect to dx.
And
You're left with the change in area. You divide volume by.
you take the derivative of this. Is it what you're saying? With respect to x? No. You have to take a derivative, but you are not. If you have the lecture notes, just go through the lecture notes. There is a slide on there that is about the Stokes theorem and integral conversions. And you have your answers there. If you want to get the bonus points, what is it? Okay, let me pull up the slide right here. This is the slide. No one? Okay. How can we combine these 2 integrals? The integration, the integrand, has to be the same. We have to take the integral with respect to either volume or area, right? Which essentially means that we have to convert one of the integrands to the other one, right? And these 3 are 3 conversion mechanisms, right? See, this one is converting a linear integral. It's a linear integral over a curve. That's why you see this circle here, right? And the C here. It's converting this to an integral over area. This ds, this derivative of the surface. I usually use A to make sure you are not confused. See? ds, derivative of a path, essentially, of a line, derivative of the area. This one, the divergence theorem, we have the derivative of area converted to the derivative of volume. Then the gradient theorem does the same thing, but for a scalar value, not for a vector. Okay, so I hope we all understand what it is that we want to do today. Right now is we want to convert one of the integrals so that the 2 integrals have the same integrand, right? Have the same ds or dv, right? And then one of these 3 is the way to go.
Divergence theorem?
Divergence theorem, thank you. Robert will get the bonus points. Okay, let's write the divergence theorem. The divergence theorem tells us an integral over a surface of any vector A, dA, let's call it vector B, can be converted to an integral over volume when you take the divergence of that vector, right? Which essentially means that we have to take this and apply the divergence theorem. I have to take the flux term and apply the divergence theorem. So how will this change when you apply the divergence theorem? Let me write the left-hand side of it for you. Integral over a surface rho v n dA. Right? Is this what you're saying? What happens with the surface normal? Since we are moving from a surface to a volume, surface normal doesn't really exist anymore. We are not talking about the surface anymore, right? So surface normal will just fly away. Does this make sense? Okay. So let's rewrite this equation. 0 is equals to the rate of change of rho dV over the contour volume plus the integral over the contour volume del dot rho v dV. Okay? Has to be equal to 0. So can we combine the two integrals now? No, because of this derivative. These are not the same integral yet. So one thing we can do is to bring this derivative inside the integral, and this is the only way to go forward actually. But we are making an assumption here, and that assumption is this element of area does not change with respect to time, meaning that there is no deformation in your contour volume, right? Which is a very, very good assumption. Let's say you are applying this to a rocket engine or into an AC duct or whatever. The volume of that AC duct does not change with respect to time, right? Because it's a constant contour volume. So no deformation inside the contour volume, which is usually the case. We can bring this in and take the integral like this. These are essentially, they have the same integrand. We can combine the integrals to 1. Okay, so the result of this integration is 0. What can you say about whatever is inside this integral? This also has to be 0, right? So we can just remove the integral. Differential form of conservation of mass. Was it?
Why were we allowed to make the assumption that EV has to be?
We are not allowed to make it. We did make it. So if you have a deformation in your contour volume, you cannot make that move. You have to, I mean, eventually you can get to this, but that way to get to this, you have to go a little more deep. Okay?
What is this form called again?
Differential. Like the differential calculus, integral calculus, it's differential. And this is a form you probably have seen in your aerodynamics, rocket propulsion. Definitely have seen this in rocket propulsion. Or fluid mechanics class, depending on what your major is. Okay. What will happen to this equation in an incompressible flow field? What is it? Exactly. So there is no change of density over time. So the first part is going to go to 0. And we can also take this out of the divergence, right? Because it's just a constant value. And then we can just drop it because on the other side we have 0. So for an incompressible flow field, the divergence of velocity has to be 0. Right? Can we expand this? Yes. What is the expansion of divergence of velocity? In Cartesian coordinate systems is partial u, which is the x component of velocity, partial x, partial v, that's a small letter v component of velocity vector, partial y, plus partial w, partial z, equals to 0. Any questions? What do we call this equation? So I guess one of the more famous equations in fluid mechanics. What is it? Here. It's here. It's on your tongue. And the tip of his tongue. It starts with a C. Exactly. Continuity equation. No, I'm sorry, not for this one. Do we have any questions? There is another way we can actually describe the conservation of mass in a system, right? And that is by using a mathematical operation again called total derivative. Total, substantial, or material derivative. Total or material. Do we remember from our mathematics what total derivative is? No, that's all right. So from this point of view, the conservation of mass is like this. The total derivative of density with respect to time is always 0. Okay? But what does a total derivative mean? The total derivative is something that you don't really see in solids. You see mostly in fluids, aerodynamics. Wherever you deal with, wherever you actually deal with diffusion and advection, right? You don't really see that in solids. Okay? What does it mean? It says the changes with time has two different components. It's not just change of a variable, a parameter with time. It has another component. So changes with time has two components. The first one is a temporal component, or a temporal means time dependent. temporal component or a time-dependent component. And the other one is a spatial component. So location dependent or location dependent component. This is a little counterintuitive because how can change in time depend on your location and changes in location. So two different components, temporal and spatial. What does this mean? Let's think about temperature, your body temperature. You're sitting here, if this AC starts working, your body temperature, I mean the temperature you feel, will rise, right? If you turn on the heater, right? While sitting. That's the temporal change of temperature, right? You're not moving, you're just sitting somewhere, and your body temperature changes in response to the elements, I guess, right? To the heater. But let's say there is no heating happening, right? Let's say you just start moving to the outside. Outside has a different temperature, right? Because of this location change, your body temperature, the temperature you're going to feel is going to change, right? That also is happening over time because it takes time for you to go from this location to a different location. So that is also the changes of temperature with respect to time, right? And that also depends on how fast you're going outside. If you go very quickly, your temperature with respect to time is going to be rate of change of temperature with respect to time is going to be higher because your body temperature will drop quicker, right? If you go very slowly, the temperature change is going to be smaller, right? The rate of change of temperature because the drop happens at a slower pace. Does that make sense? So the idea is the change with respect to time has two components, a time-dependent term and a space-dependent term. Mathematically, though, this means that if you want to expand this material derivative, it has a time-dependent component, which is this one, temporal term, plus the space-dependent component. So this is the spatial term. This is the temporal term. So, and change material derivative of density with respect to time is always 0. That's the idea. You can also expand this. Let me write it down here. I'm writing the same thing down here. We can also expand this and write this. What is it? Rho. Density. We are dealing with density. There's no pressure here. For pressure, I always add a line here. This is pressure. This is density. This is rho. This is P, I guess. How do you write P? P. What is it? These are all partials. This is just expansion of this term. U partial rho partial x in the x direction. This is in Cartesian coordinate system. V partial rho partial y, W partial rho partial t. This is These are our partial derivatives. So 3 different ways of looking at conservation of mass. There is one bonus point here for those of you who are interested. As you can see, this equation is different from this equation. if you expand this, this is going to look like this. Partial rho u, partial x, partial rho v, partial y, partial rho w, partial z, equals to 0. Right? These two do not really look like each other, but we are saying that these are the same equation, right? So the bonus point is to get from this equation to the original conservation of mass equation. So go from the material derivative perspective to the differential form. You essentially want to prove that this is the same thing as the differential form. These are similar. And for this, you are going to get 4 bonus points, which is equivalent to 2% of your grade. Each bonus point is worth 0.5%. Right? There will be a submission portal open on Blackboard, and you have to do this by Wednesday. Here? Okay. How many of you have 0 understanding of what went on today up until this point? So everyone understood at least 11. 50%. Just 50, not more than 50? Where is the confusion? What do you understand? I assume the rest of you have more than 75% understanding, right? Where is the confusion? What don't you understand? I mean, these are just proofs. You can't really have examples of these. I mean, they're going to use conservation of mass in different examples, but to get to this point, it's just mathematics, right? But did you follow the procedure? So that's what I'm asking. Were you able to follow the procedure? Which part didn't you understand? That's alright if you don't know what to answer. But if you do know, yes.
So I have some confusion. Starting from the v vector dot and the normal surface normal.
Yep.
Yes. Why did we both make that for gradients?
Okay, let's go back to this control volume again. We said this is what we had: 2 inlets, 2 outlets, right? Okay, and the equation we had it was double integral over all of these surfaces. We said let's generalize this equation a little more, so we have all of the surfaces together in one general equation instead of just writing out each surface separately, right? So what we did was we said if you take the dot product of the velocity vector with the surface normal, which is a unit vector pointing outwards, normal to the surface, that sign will appear automatically, right? For example, for this, in our original equation, we had a negative value, negative sign just behind the integral, right? So rho v dot n dA. We had negative double integral of rho v dA, right? Let's take this dot product, which is magnitude of v, magnitude of n, cosine of theta. This is 1. This is just v, whatever the magnitude is. Cosine of theta here is negative 1. So you get a negative sign here out of this dot product, right? Negative v. I'm going to write it down here. So we're going to have double integral of rho negative v dA. I'm going to take the negative sign out. which is what we wanted, right? Same thing can be applied to the outputs. I will give you a positive value. Okay, so let's talk about the momentum equation. At this point, you have at least seen all of the mathematics you need to know to find the momentum equation. So momentum equation comes from the second Newton's law. What is the second Newton's law? Sigma F is equals to mass times acceleration. Does this apply to fluids though?
No. Not in that form.
What is the form? What is the correct form though? So in fluids, the idea is this mass can change, right? In general. Density changes, volume changes, all of those things. So in a fluid, let's say if this is your solid, if you apply a force, all of this will move together. But if you apply this, if this was a fluid wall, if you apply the force to this fluid, it wouldn't move like a solid. Meaning that we cannot assume this mass is constant. The general form of the Newton's second law is like this. Let's get there. So this is mass, derivative of velocity with respect to time. And then what I'm saying is that we have to take mass inside this derivative. We cannot take it out. Okay? The most general form of the second law is the derivative of mass times velocity with respect to time. And this is mass times velocity of a system. Okay. What do we call this variable? Mass times velocity. Momentum, right? Exactly. So the idea is the second law for the most general form of the second law is the rate of change of momentum is equals to the summation of all of the forces that are exerted on a body, on an object, or on a fluid. Okay, so, and again, this is the rate of change of momentum of a system. Okay. We have seen this form of derivative before. This is a total derivative. We also saw it in the Reynolds transfer theorem, right? So let's use the Reynolds transfer theorem and just replace B with the momentum this time. I'm going to do a reminder here. The Reynolds transfer theorem said the rate of change of a variable B in the system is equal to the rate of change of the same variable in the control volume, and the fluxes plus the fluxes out of or into the control surfaces. Okay. So the only thing we really need to do here is to replace this with the momentum. So momentum of a system. So B, capital letter B here, is momentum, mv, which means that the small letter b is going to be just velocity, v, right? Okay. This is the rate of change of momentum over the control volume. So rho v dv plus the fluxes out of and into the system of momentum. Rho v dot n dA. And based on the second law, this has to be equal to the forces that are exerted on your body. This is the integral form of momentum equation. Any questions? Let's say I ask you to do the same thing, essentially find the energy equation for me. How would you go about just using the Reynolds transfer theorem? How would you go about finding the energy equation for us? First of all, the first step in finding the energy equation is writing down the first law of thermodynamics. What is the first law of thermodynamics? And this is just let's call this a side note. What is the first law of thermodynamics? That's exactly, but we are looking for a small element of it. So changes of the rate of change of energy again. So E, or let's make it a small e, is Q minus W, and these are in watts, right, not joules. Which essentially means that this is going to be your energy is going to be capital letter B. If you want to find the energy equation, you have to replace this with the energy dt, and then set it equal to this, equal to the integral for the energy. Then you have to find all of the heat and the work that are added to the system and done on the system. But energy equation is outside of the scope of this course, so we are not going to focus on it. Okay, do we have any questions so far? No. So next step for us is to find the differential form of this equation, right? What should we do to find the differential form of this equation? What did we do last time? We said we have to combine all of these integrals into one integral, right? And here, this is not equals to 0, this is equals to sigma of f. So we have to come back to the sigma of f and fix the problem with the sigma of f as well. We have to essentially find all of the forces that are exerted on any control volume, right? But that is, I guess, next lecture's step. Right here, we want to combine these two integrals into one integral. How should we do that? The divergence theorem, right? What did the divergence theorem tell us? The integral of any parameter, in this case we are dealing with the momentum specifically for us, right? So this velocity essentially, rho v dot n dA can be converted to a volume integral if you just take the gradient of it. And again, since we are changing to a volume integral, this dot product with the surface normal is not going to exist anymore. because we don't have a surface anymore, we're dealing with a volume. So your momentum equation you're just going to replace the surface integral with the volume integral. And this is equal to sigma of f. And again, we are going to assume that there is no deformation in the volume. I'm going to take this inside. Let's combine it. You are not at the final form of the differential form of this momentum equation, because we still have the integrals and we still have an unknown sigma of f. So we're going to come back to this because we still have time. We're going to come back to this next lecture and talk about this.
Are we implying dot product being used between two velocity vectors?
What is it?
Or what kind of operation are we applying between the two velocity vectors in the second half?
It is actually to have the most correct form. This has to be outside of the gradient. So you are taking the divergence of this multiplied by the velocity vector. So that would be just a scalar, right? Multiplied by velocity. Any questions? Okay. We still have 15 minutes. We can finish this discussion, but I get a feeling like that they have had too much mathematics for today, right? A lot of mathematics. Nothing new though, right? These are just reviews of fluid mechanics and aerodynamics, right?
That was a couple years ago.
No, some of it is new, I know. But yeah, so I guess let's just stop here for today. We're going to come back Wednesday, and continue the discussion. We're going to finalize the momentum equation, and we're going to solve a couple of example problems to help you guys understand this better. Right? We're going to apply this to a couple of examples, essentially. And this is, keep in mind, on your first exam, you will definitely get either the conservation of mass, the proof of conservation of mass, or the momentum equation in your exam. Does it make sense? Yes.
When you say we would get it in the exam, you mean we will?
It'll be a question on the exam.
There'll be a question on the exam.
Yeah.
Just make sure.
It will definitely be yes.
Is it going to be finding the integral form, the derivative form, or both?
The differential form. So I mean, this means that you either have to use the material derivative or you have to find the integral form first and then go to the differential form. Yes.
So then that would mean like the one expression that we talked about go from the material to derivative form, that's what we have to show them.
No, on the exam, no. No, that would be a little difficult. But the thing is, you can include all of these in your cheat sheet, right? The only thing you cannot include in your cheat sheet on the exam are solutions to example problems. And derivation is not a solution, right? It's a solution to an exam problem, but it's not a real solution, right? I don't really mind if you include this in your cheat sheets. But at the same time, if you don't understand what is going on, even if you include it, you won't be able to give me a correct answer. So, yeah, that's it for today. If you have a question, I'm here. And you need to join. So we need, just give me 1 second. Matthew, right?
Yes.
Matthew needs to join one of the teams. I guess we are going to have another team with 4 members. Who is willing to take Matthew on?
Are they all the same size?
Yeah, there are the 3 to 4 students.
Oh, then I'll just take a pic of the coworker.
What is it?
Can I just join David's?
I think David already has 4 of you. How many do you have in your team?
Oh,
You
yeah.
have 3?
Cool.
Yes. Yeah, Horton has a question. Horton, you had a question, right? Guys, talk to your teammates. Yes, David.
I just had a question about this M part. When you're using the divergence theorem, like, how do we get this additional V? Because, like, rho V is.
Right here in the main equation. You have 2 V's. This is also a vector.
Oh, okay. Oh, okay.
Yeah. Yes.
So,
No way.
I wanted to know how in depth you wanted this to be. If you wanted this to be more than that, that's fine. I've been in intermediate dynamics, I'm like finally understanding this. So that actually does, that is about, I did all the steps I could think of, which is that this is the gradient multiplied by the.
But this is not correct.
Oh,
You shouldn't have these unit vectors at the end though.
no?
And you have already done the dot product, right? And when you do the dot product, those unit vectors will go away. This is I, J, and K, right?
Okay, so they stay here but not here.
Now, if you do the dot product, what is the dot product of I and J? 0, right? Dot product of I and I is 1. You just have to write it out for yourself. But what you have over there is wrong. It's very wrong. Just do the dot product first. If you couldn't figure it out, just we can talk again and just go over
I
it.
mean, this is just like in between.
What is it?
Like I just did this like in between
Yeah,
other
so
things,
this is
so I'll
good.
actually.
Yes. So, yeah. I'm sorry. Let me just stop this recording.